Hello, and welcome to the mini course on the Dirichlet series as part of the GN Lewis project. My name is Darren Olmus. I'm in the Department of Chemistry at Concordia College in Moorhead, Minnesota, here in the United States. And I live my professional life really based around this very famous quote that's in pretty much every physical chemistry book. And it says that physical chemistry is everything that's interesting. And this is by G.N. Lewis, famous physical chemist. And you could read that two ways. You could read it in a more cynical way, saying that anything worth studying is just physical chemistry. But I read it in a much more expansive way. And I read it as learning physical chemistry gives you the ability to look at the world in such a way that you can investigate all the things that you're interested in when it comes to trying to understand the universe we live in. And I'm very interested in mathematics. I'm interested in really all math. There's not really any areas of math that I don't like, but I particularly love complex analysis. And of course, complex analysis is used with great power throughout physics and chemistry. But there's a niche of complex analysis that has really cool connections to number theory, and we don't see as often. Of course, it's there in physics. Pretty much every area of math has been used at some capacity, but we don't really run into as often some of the things dealing with complex analysis and its relation to number theory in physics. And so one of those things is the Dirichlet series. The series itself is this. I've heard it pronounced by, I think, people who know what they're talking about as Dirichlet. So the Dirichlet series. We're going to use this symbol for it. It's a function of complex S and some set of coefficients, Dirichlet coefficients. And it's simply this series right here. So we're going to study this series a little bit, just scratching the surface. There's an enormous amount of information in analytic number theory about this, but we're going to just look at some of the basic properties and then try to connect that to a little bit of physics as well. So the first lecture we're going to prove, and this brings up what I should say about the level of rigor of this course. We're going to come at this from the perspective of a physical chemist. So we're not going to we're not going to treat this with extreme mathematical rigor. So we're not going to be talking much about checking whether you have uniform convergence of these series and other things like that. So that can we really switch the order of two summations or switch the order of integration and summation? We'll do like we tend to do in physics and chemistry and just switch the order as convenient. Other areas in terms of proofs, really we just want to come away with, or I want you to come away with just getting a sense for this. So we won't give rock solid proofs. We'll kind of talk about it in ways so that we can intuitively understand, and you get the gist of either the gist of the proof or just through some examples you can kind of see how the proof would go. So that's the level of rigor that we'll be at through the course. So we'll sort of prove the Euler product, which is really important, and we'll use that quite a bit. And then we'll get introduced here to the Riemann zeta function. And the big job of lecture one is to go through a bunch of manipulations of the Riemann zeta function. And really that's to develop some skills on how to attack these types of problems. Then lecture two, we're going to talk about multiplying two Dirichlet series and this process of zeta function regularization. And this is a way to take a divergent series and get a useful number out of it. Now, it's not sort of mathematically legal, but it often works, and it has had great success in quantum field theory. Then the third lecture will be the Mellin transform, and this will be very useful in connecting us to physics. So we'll see that through the Mellin transform, we can obtain the partition function from statistical mechanics. And so there'll be a relationship between the partition function and these Dirichlet series through the Mellin transform. And then finally, we're just going to talk about just some crazy quantum model that I made up based on the Dirichlet series, which I'm calling here the tau quantum system. So this is not a real quantum system, at least that I'm aware of, just something that I made up as a working example here. Now, there's a lot more we could have done, especially in the Dirichlet series. There's something called the L series, or the L functions, the Dirichlet L functions. And I may later, if you're coming to this playlist, many months or years down the line, maybe I'll add to this talking about the L series, or we'll just make another mini series on that. So big portion is missing there. And again, we'll only scratch the surface. I mean, whole books can be worked through on pretty much each one of these lectures. All right, so hopefully you're kind of excited to maybe learn something new. If you have been learning a little bit of physics or chemistry but haven't ever run into the Dirichlet series or the Riemann zeta function, then hopefully you'll get something out of the course. And so I'll see you in the first lecture.